A byproduct of this bagging or random forest technique is the fact that it's possible to compute we have an easy way to compute an error for bagged or random forest models that we obtained in the previous videos. In fact, the bootstrap techniques makes that in bootstrap samples, it's possible to have data that are not used by every bootstrap sample. And we are going to explore the fact that data are not used by bootstrap samples in order to compute an error, a prediction error for a bagging or a random forest methodology for the application of one of these methodologies. What we can say first, for that we are going to first try to characterize a data which is not used by a bootstrap sample. When we have a bagging or a random forest procedure, we have B bootstrap samples, B trees that are constructed, and the question is going to be, okay, for a given data, how many trees use these data to construct the different steps of the resulting trees? Thus my question is, okay, how many trees do use the data, let's say data I? Therefore, to understand that, first we say, okay, for a bootstrap sample S, let's name it S of size n, what is the probability that the data j in this case, the jth observation in the original sample, what is the probability that j, the data j, belongs to the bootstrap sample? This is 1 minus the probability that the j's observation in the original sample does not belong to the bootstrap sample S. What is the probability that j's observation does not belong to sample S? At each draw, we have a probability 1 over n that the jth data is sampled, is drawn. Thus, in a bootstrap sample, we have n independent trials, n independent draws. At the first draw, the probability that the j's observation is drawn is 1 on n. At the second draw, we have a probability 1 on n that the j's observation is sampled, and so on. The probability that j is never sampled. What is the probability that j is never sampled? This is the probability that j is not sampled at the first draw, not sampled at the second draw, not sampled at the third draw, and so on. And since these draws are independent, we have a product of this probability that j is not sampled at a given draw. Therefore, the probability that j is not drawn at a given draw, what it is? This is 1 minus 1 divided by n. The probability that j is not drawn at a given draw, the j has a probability 1 on n to be sampled. Therefore, the probability that it's not drawn at this given draw is 1 minus 1 on n. Therefore, the probability that j is never drawn is the probability that it's not drawn at the first draw, not drawn at the second draw, and so on. These draws are independent. Therefore, this is equal to the product of probabilities. Therefore, we have 1 minus 1 on n to the power n here. That this is the probability that the j's observation is never drawn for the bootstrap sample S. And therefore 1 minus this is the probability that the j's observation is drawn is in the sample S. And what is this probability? If you compute the limit for 1 minus 1 over n to the power n when n tends to infinity, this tends to exponential of minus 1. You can compute it by yourself. Use exponentials and logarithms. This can be considered as an approximation of this quantity for n sufficiently large. And what is this quantity approximatively? This is 0.632. That means that the probability that a given observation is inside the bootstrap sample S, this is around 63%. That means in general, then in a bootstrap sample you have around, that is our conclusion, in a bootstrap sample we have around 63% of the data that are in the initial sample that are found in a bootstrap sample. This is in average, this is a mean, but we can think the different steps with this information. First tool, thus, we have 63% of around 63% of the data of the original data set that are found in the bootstrap sample S. Does that mean that, okay, they are for a given sample, there is around 37% of the data that are not used. That means that data also, in the same way, is not found in around about 37% of the samples. A data, therefore, let's consider this data. Let's take one data. One data is not observed in about 37% of B, the number of bootstrap samples. Let's name these samples where B, let's count these samples where the data I, these bootstrap samples where the data I is not observed. For what is the amount, okay, for the data I, let's say for a data I, we are going to see what is the number of samples where the data I does not appear. We are going to say that there are B minus I samples, B minus I bootstrap samples where the data I does not appear. And BI is around about 37% of B. This observation I is named an out-of-bag observation for these B minus I samples where the data I therefore is not included. That means that the trees that are constructed for these B minus I samples do not use the data I. Therefore, the data I can be used to evaluate the quality of the trees that do not use for these B minus I trees. Data I can be used to evaluate the quality, the predictive ability of these B minus I trees. Therefore, okay, we are going to find data I is an out-of-bag observation. Therefore, we are going to see what are the predictions of this data I obtained with the B minus I samples. And therefore, we have here an estimate of the out-of-bag prediction, F out-of-bag prediction. What is that? This is 1 divided by B minus I, sum over B over all these trees of the predictions obtained by each of the B minus I trees. B minus I trees, and here we have the index B. The index B, this is the index of a bootstrap sample, and here we only take in this sum the indices of the bootstrap samples for which here B minus I, here as we can see, is the set of sample indices for which the corresponding sample do not include data I. In classification techniques, no problem, it's almost the same. We have also out-of-bag data. We are going to take xi, we are going to take the b minus I samples corresponding to xi. We are going to see for each of these trees what is the class which is predicted for this data xi, and then we are going to count, we are going to make a vote, and we are going to see what is the largest amount of vote, what is the class, what is the winning class, what is the winning class for this data xi. And therefore among the b minus I samples there is a class which is winning, that means for which we have the largest amount of trees that predicts this class for the data, a large amount of trees that predict this class for the data I. Therefore, we have a prediction for an out-of-bag observation, here f star out of bag for xi obtained by the different trees. That means that with these predictions for or predicted values for the n data points, it is then possible to compute an out-of-bag error. An out-of-bag error which can be understood in a very easy way. This is a sum of squared for all the data of the original samples. We have the true yi that are observed in the initial sample, and we have the predicted values for these yi that are obtained with the trees that do not use the data xi. This can be considered as an estimate for the error, the test error in regression. In classification, this is almost the same thing as well. We have one class which is predicted for each out-of-bag observation. We have b minus I samples for the out-of-bag observation xi. We have from this b minus I trees, we have a class which is chosen for all these trees. We have therefore through a majority vote, we have a class which is chosen for the b minus I trees. Thus what we only have to do is a misclassification rate among the n data of the initial samples. For the n data can be considered as each data of the initial sample is an out-of-bag observation each time for b minus I samples. Therefore, for each data we have a predicted class, and we just have to check if this class is correctly chosen or not. And thus we have a misclassification rate, the number of data in the initial sample that are not correctly classified by the b minus I trees for the data I. Thus we have something in each case, regression or classification, we have something that estimates the test error, and we can show that these estimates for b sufficiently large, these estimates are close to the estimates for the test error that we can obtain with leave one out cross validation.